Okay, in this segment, I want to just go over some data on resistor matching, just to kind of inform your intuitions about component matching. The first source of data I'd like to share with you is a couple of episodes of the EEV blog that were produced by Dave Jones a few years ago. I'll put the links to these videos in case you're curious about them, to review them. I think actually he's very entertaining to watch. If you've never been exposed to the EEV blog, you might want to check it out. But just the way that he, especially at the beginning of the second video, the way that he decided to do his setup to actually take these recordings efficiently is actually pretty interesting. So that's just something to think about doing if you have the time. But he took standard metal film resistors with a tolerance of plus or minus 1%, like we typically use in like iSim or have in the stock room. And he asked, well, what does the distribution of these resistors actually look like? I mean, is it uniform between minus 1% and plus 1%? Is it something else? And so he actually took a tape that had through-hole 1% resistors from Philips, and he measured 400 of them with the same multimeter, and he recorded sort of a normalized variation, and he adjusted things so that 0% is the nominal value. And for these sample of 400 resistors that he measured from the same tape, which were presumably manufactured at the same time under the same conditions and packaged up in the same sort of bandolier, he found that this is what the distribution looked like for those 400 resistors. And it looks like a fairly nice Gaussian curve, sort of a bell-shaped curve with some tails here. And instead of being anywhere near the plus or minus 1% variation, you find that the maximum variation that he found was basically plus or minus 0.5%. And he didn't actually quote the standard deviation of this distribution, or the sample that he took. Would have been nice if he had, but if you look at how many samples, like what percentage of the population was captured in each of these bins, you find probably the standard deviation is going to be in the range of plus or minus like 0.175%, or maybe plus or minus 0.18% or something like that. So if it is an actual Gaussian, then plus or minus 1 standard deviation captures about 68% of the population. In other words, the area under this curve is about 68% of the total area under the curve. And if you go out 2 standard deviations plus or minus from the mean, that captures about, I think it's 95% of the total population. And if you go up plus or minus 3 standard deviations, that captures basically 99.5% or something of the population. And so people talk about Six Sigma manufacturing, where basically if you can limit that standard deviation so that you control plus or minus 6 standard deviations, and that fits within your tolerance, then you're guaranteed to basically be within the spec. And so these people who manufacture resistances apparently have set up their manufacturing process so that they are manufactured to quite a bit better tolerance than the plus or minus 1%. So I mean, you can actually move this mean around a little bit within this window and shift this curve to the left or the right, and you have a good margin of safety there. He did a similar kind of experiment in the next episode. Let's see if I can find a screenshot from that one, where he looked at a Chinese manufacturer instead of Philips. Again, 1% metal film resistors, and he found kind of a similar thing, only there was a systematic shift in the mean away from the nominal value, which would be, again, 0%, so that it's biased a little bit to slightly lower values. so it's minus 0.3% away from the nominal value. But again, that distribution is pretty tight. So if you pick a bunch of resistors from that same lot, it's very probable that they will match each other. In other words, the resistance may not be exactly the value that was specified by the nominal value, but they will be very close to each other. And again, the standard deviation is not something he quoted for this particular sample, but it's probably, again, in the ballpark of maybe 0.1%, 0.15%, something like that. So that's one source of information about resistor matching. The other source that I'd like to share with you is something that we've done in this class in the first lab historically. So historically in Lab 1, students in the class have used what are called thick film resistor arrays made by a company called Bourne's. They've used 10 kilo ohm resistor arrays. So these are basically 8 thick film resistors that are packaged together in the same dip package, and the leads are just straight across. So pin 1 and pin 16 are the first resistor's leads, pin 2 and pin 15 are the second resistor's leads, and so on. And one of the things I've had each group do is take 2 resistor arrays and measure the resistance with a very nice bench instrument that measures resistance to something like 5 significant digits, and record those values in a table. And I've given them like some bonus points for sending me these data for their 2 resistor arrays in a CSV file so that I can compile them and show them the distribution of the resistor values. And so what I've got here is a plot that I made from the data that was sent to me back in 2012. And I forget exactly how many samples there are, but there's roughly, let's say, between 20 and 30 resistor arrays that are tested, and each one has 8 resistors on it. And so this represents something like, on the order of, let's say, 100 samples or something like that. And you can see, so the resistance nominally is 10K, and the manufacturer specifies in the data sheet for these parts a tolerance of plus or minus 2% in the absolute resistance value that these resistors will have. And so what I've shown here on the horizontal axis is 10K in the middle, plus or minus 2%, which would be 200 ohms for 10 kilo ohms. And so you can see that all of the resistors that were tested in this batch in 2012 fell nicely within that range. In fact, the distribution is actually fairly tight, except for this maybe one outlier here. And it has a kind of a bell shape. And if you divide all of the resistances by the sample mean to normalize everything, I've shifted the distribution and made what I'm calling here normalized resistance, and showing you a histogram of that. And you can see that the standard deviation divided by the mean of this, which is 1, so it's just the standard deviation of this normalized resistance, is about 0.1%, which is quite a lot tighter than the plus or minus 2% that you might expect based on the tolerance specified by the manufacturer. And if you go further, and instead of normalizing each of the 100 resistors to the overall sample mean, if you take each group of 8, which represents the resistors on a single chip, and then normalize each chip to its own sample mean, what you find is the distribution is even tighter. So it knocks the tails down a little bit and makes the distribution tighter. Instead of being about 0.09% for the standard deviation, it's 0.08%. And so it's generally speaking a principle that we will rely on in designing integrated circuits that, like devices that are manufactured under nominally identical circumstances, that are packaged in the same chip are likely to match each other very well. And so the better matching of these resistors within each array, rather than the group that was manufactured around the same time and maybe came in the same tube of chips and things like that, is a manifestation of that. So if we go to 2013, you can see a very similar kind of result. A little bit more spurious values up here that are kind of outliers, but again, the distribution is a lot tighter than the plus or minus 2% tolerance on the absolute value specified by the manufacturer. And here, again, we see that the normalized resistance per array is tighter than the normalized resistance for the whole population that we sampled that year. One thing you can see is in these data that there's always there's some outliers here, like this one way off here to the left is probably actually outside of the tolerance band specified, and it just gets moved over here when we move the sample mean to 1 here. And that probably is a measurement error. So I asked the students in the class to use this one particular bench instrument in the instructions, and sometimes they just get out a craptastic multimeter that they find lying around someplace and use that instead of the nice bench instrument, and they probably wind up measuring something that's in the ballpark, but it's not calibrated to NIST standards and doesn't give you 5.5 digits of precision or something. So I have a feeling those outliers are more due to students in the class not following the instructions than they are to actual variations in the resistor values. So we'll have to some extent discount those. But that was 2013. This is 2014. You can see here there's maybe a second mode. So we have one sort of peak here, and then we've got a smaller peak here, and that's probably, it could represent maybe some chips that were left over from a previous year mixed in with chips that came out of a fresh tube or something like that. But you can see still the same kind of thing where it's a fairly tight distribution for the most part compared to the plus or minus 2% tolerance. And if you look at the normalized resistance per array, you find that the coefficient of variation is actually quite a lot smaller than the overall distribution coefficient of variation, because again, we don't have these two separate modes here when we normalize per array. So this is 2015. Again, you can see some more spurious values here, but again, we have this sort of tight distribution, and the coefficient of variation is smaller normalized per array than if we just normalize the whole thing to the sample mean. 2016, same kind of thing. 2017, I'm not sure what happened in 2017, but in the 2017 case, the mean value seems to have shifted down substantially compared to where it's been, which is more kind of in this range in other years. But again, we see a relatively tight distribution compared to the plus or minus 2% range specified for the absolute values, and we can see that the variation within an array on the same chip is substantially less than the variation in the whole population. This is 2018, same deal. 2019, same deal. 2020, same deal. And so this is basically the whole enchilada. So I just put all the data from all the years in one giant spreadsheet, and I think there were about 1,600 resistor values in this sample. And so you can see, there's sort of, most of the population is kind of in this range, but then in 2017, where we had that one group that was kind of off down a little bit to a slightly lower value of mean resistance, that represents this mode here, and the rest kind of stack up in more in this range here. And again, if you normalize per array, you wind up with a much tighter distribution than the overall distribution. Now it turns out that this coefficient of variation, which says is 0.26% compared to the 0.38%, you might think that this distribution looks a lot tighter than is reflected by these numbers, 0.26% versus 0.38%. And if that is your intuition, I think you would be right. The thing that's contributing to this 0.26% down here are these little tiny things that you can barely see. So down here at minus 2%, you can see these values, and you can see some of these very faint little tiny peaks, which are probably just like 1 or 2 resistor values. And those things are contributing to the spread, even though most of the distribution is really, really tight. So if you exclude everything outside the range of plus and minus 0.5%, the coefficient of variation that you get for just this part of the distribution winds up being 0.08%. And if you include things out to plus or minus 1%, it turns out to be 0.13%. And so this distribution is actually quite a lot tighter than this. And in the case that we exclude everything outside of plus or minus 0.5%, I think, if I remember correctly, it was 40 resistor values out of 1,600 were excluded when we chopped out all of these. And if we went out to plus or minus 1%, I think we only excluded like 7. So 7 out of 1,600 resistors are contributing the difference between 0.26% coefficient of variation and 0.13% coefficient of variation. And if we throw out the ones that are kind of in the range of 0.5% to 1% in that window and this window here, that's again not a whole lot of resistors in the whole sample. So the matching of resistors within an array is actually quite tight. And the way that we would normally have students do the experiments in Lab 1 is to use resistors in the same array. And so the matching is actually pretty good. But I usually ask people, if let's say the resistive voltage divider ratio that they measure is commensurate with the matching that they see, or the degree of matching that they see in their table of values. Obviously, I am not able to have you guys do that this year in simulation. So instead of asking you to measure a batch of resistors and see what the variation is, this year instead we're going to ask you to perform what's called a Monte Carlo simulation. And so there'll be another tutorial video, LT Spice tutorial video, coming out in time for Lab 1 that will lead you through how to do that and how to set it up. And you'll be looking at kind of for one of the experiments, not all 3 of them, but for one of them you'll be looking at sort of the distribution of, let's say, voltage divider ratios or something like that you get when you draw the resistor values from a normal distribution with a certain standard deviation about its nominal sort of mean value. And we'll use this data, or these data, as a basis for picking what that standard deviation will be. Okay, so that's the data that I wanted to show you on resistor matching. Like I said, I'll put the links in the week's page to the EEV blog videos in case you're interested. One more plot. This is a plot of the mean values in each array, and these are not the series of values here is basically rows in my spreadsheet. So all of these rows were from 2012. All of these rows are from 2013, 2014, 2015, 2016, 2017, 2018, 2019, and 2020. And so you can see that, the mean does shift from year to year to some extent, although, between these 2 years it didn't shift very much, and it shifted quite a bit down here, and then it sort of shifted back, and it's been fairly stable here over these 2 years. Why that is completely unknown. I mean, it could be that the manufacturing process does shift from time to time, and it kind of goes up and down, and we're sampling it, at 1 year intervals here. But you can see that 2017 was kind of a strange year. We had this very large jump in the mean value here from up here down to here, and there's quite a number of spurious values. So the sample means from these two chips are kind of contributing to our outliers. In 2020, this would be 2015, we had this one, which was a really big outlier compared to the sample means up here. This could be one group that decided to use their craptastic multimeter that they found lying around with a dead battery, as opposed to the one that was specified and whatnot. But anyway, so that's the data that I wanted to share with you. And like I said, you'll be doing some Monte Carlo simulations for one of the experiments in Lab 1, and so I wanted to show you some actual data that has been taken by your predecessors in this class that will be feeding into that experience. So this will be a shorter segment, and we'll see you next time.